Hello and welcome to College Physics 1, Lecture 15, Equilibrium and Newton's Laws. So in our last lecture, we took a look at Newton's three laws of motion. The first law basically states that an object at rest will remain at rest and an object in motion will remain in straight line motion at a constant speed unless they're acted on by another force. Newton's second law said basically in mathematical formulation F equals ma. Newton's third law states that every force occurs as a member of an action-reaction pair of forces. In other words, you commonly hear this that for every action there's an equal and opposite reaction. So we see forces occur in pairs that are equal and opposite. Our goal in this lecture and the next is to take Newton's second law, that is F equals ma, and start to apply it to solving problems. So the goal of this first lecture on equilibrium is to think of the simplest possible case. When we talk equilibrium, we mean an object that is either at rest, hence we call it static equilibrium, or an object that's moving in a straight line and in a constant speed. In that case, the object would be in dynamic equilibrium. But in either case, whether it's at rest or moving at a constant speed in a straight line, it is still considered equilibrium. So think about what this means. If you're at rest, you are not accelerating. If you're moving in a straight line at a constant speed, you are also not accelerating. So for both of these cases of equilibrium, your object is not accelerating. Its acceleration is zero. So if you take a look then at, say, Newton's second law, which says F equals ma, well, if the acceleration is zero, you're plugging in a zero into this equation, which means your net force is also going to be zero. So, for objects that are in equilibrium, if we were to write out Newton's second law in component form, we would see something along the lines of the following. Now, this is going to be a new symbol in our class, this sigma symbol. This is the capital Greek letter sigma. So understand that sigma in math stands for the sum of. So when we take a look at this equation that we've written, this translates to the sum of forces in the x direction. Okay, so sigma fx is the sum of forces in the x direction. Now, by Newton's second law, it should equal ma. But since acceleration is zero, we can just set it directly equal to zero without having to worry about ma. So overall, these equations really are just the sum of forces in the x direction equals zero, and in the y direction, the sum of forces, Fy, are equal to zero. So we're looking at the simplest possible case where there's no acceleration involved regarding our objects. So this is equilibrium. Let's take a look at how to deal with these types of problems and then solve a few of them. So again, remember that objects in equilibrium have no net force acting on them because there is no acceleration. So let's use that idea to solve problems. Anytime you have an object that is in equilibrium, again, this is the key, we will do the following. First, just ask yourself, you don't have to write anything down on paper when working out these problems here for step number 1, but just check that the object is in equilibrium. Ask yourself, is this object in equilibrium? Which means it's either at rest or moving in a straight line at a constant speed. In other words, just ask yourself, is the object accelerating? Does acceleration equal zero? So if the acceleration is zero, your object is in equilibrium. Once you pass that barrier, just making sure you're in equilibrium, you can finally start to work on the problem. Every one of the problems we're going to do over the next several lectures starts the exact same way. Identify your forces and draw a free body diagram. This is pivotal. It is key to solving these problems. So do your best to make sure you can understand free body diagrams, because then if you don't, you can't solve the problem. Which brings us to step number 3. Apply Newton's second law as we just wrote on the previous slide, and solve for whatever force it asks for. So let's get right into solving some of these problems. We're going to work out 3 of them together. We're going to start with the simplest possible example. This is as simple as it can get. Not to say it's simple or easy, but it's the simplest that we have. So this first problem says an orangutan weighing 500 newtons just hangs from a vertical rope. It asks, what is the tension in the rope? So the 3 examples we're about to do are all going to ask the exact same question. What is the tension? But what changes is the situation. And so I think this is a really good introduction to these types of problems. First of all, let's ask ourselves, are we in equilibrium? Well, in this case, it's just an orangutan hanging there from a rope. It doesn't mention he's swinging around or anything like that, being pulled up or falling down. So the orangutan should be at rest, which means it is in static equilibrium. So we can indeed confirm that we are in equilibrium. The object is not moving. Step 2 says to identify your forces. Well, we have an orangutan hanging from a rope. Most students, or myself included, the first force you always think about is weight. Everything near the earth has a weight associated with it. So we do have a weight force. We also have, quite clearly stated in the words of the problem, a tension force. The orangutan is holding onto a rope. That rope has tension in it. And so there is a tension force as well. But that's it. There are no other forces. We just have a tension above the orangutan and its weight pulling down. So this allows us to draw a free body diagram now. Now, for the sake of clarity, I'm not going to draw it myself on the first 2 of these problems just because it's a lot easier or more clear to see if it's nice and neat. So let's just walk through how we draw this. You always start by drawing your axes, your horizontal x-axis and your vertical y-axis. Make sure you label your axes. This is important, especially later on because you're going to have to label your axes for your problem to make sense. You'll see what I mean soon. Once you draw your axes, draw a dot at the middle to represent your object, and then represent your forces as vectors, pointing away from the dot. In this case, we know there's a weight force pulling down on the orangutan, but there's also a tension force pulling up on him. This is important as well. The size of your vectors matter. There is no net force, which means your 2 forces should be balanced so that neither one is bigger than the other, so there would be a net force if that were true, but there's no net force, so they have to be equal in size. So do your best to draw, in this case, your 2 vectors the same length. Tension up and weight down. With this out of the way, we are ready to solve the problem. We're on to step number 3 of our problem-solving strategy. Every problem starts the same way. Draw your free body diagram, and then write out your Newton's second law in component form. In other words, sigma fx and sigma fy. The sum of fx and the sum of fy. Note, I never draw sigma the same way twice. They're going to vary wildly, but hopefully you can still understand what the symbol I'm writing is. So let's think about the forces in the x direction. Looking at our free body diagram, there are no forces in the x direction. So when we try to add up all the forces in the x direction, there's nothing to add up. It is just 0. In physics, zeros are our friend. It really makes things a lot simpler, or quicker at least. But in the y direction, we do indeed have forces. Keep in mind that up is the positive direction, down is the negative direction. So when we try to sum up the forces, we have tension pointing upward, so it's positive, and weight pointing downward, so it is negative. This is an equilibrium, so the sum of forces is equal to 0. Right? So again, we have tension pointing up, so it's positive, weight pointing downwards, so it is negative, and it's equal to 0 because, as we mentioned, for equilibrium problems, your net force is equal to 0. So this is it. This is the setup to the problem. We've drawn our free body diagram and written out Newton's second law. At this point, you solve. Well, these are the only two equations we have. 0, which is irrelevant, and the y equation, which says tension minus weight equals 0. Well, from this, just add weight to the other side, and you'll find that tension is equal to weight. In other words, we have our answer. The weight was given to us as 500 newtons. So 500 newtons is also the tension and our answer. Okay, so we're going to try to ease into all this material. So this was your basic example. Not a lot happened here. And in fact, you could probably reason this answer in your head before we even did the math. I mean, if the only forces is the weight down and the tension up, and they have to balance, then if one's 500, the other has to be 500. So this is the first example working with Newton's second law in component form. Now, let's do a second example that is a lot more involved. It's not terribly harder, but there's more steps involved. So let's take a look at this one. Example number 2. A car with a mass of 1,500 kilograms is towed at a steady speed by a rope held 20 degrees from the horizontal. A friction force of 320 newtons opposes the car's motion. What is the tension in the rope? Okay. First, ask if it's an equilibrium. Well, we are moving now, but it says at a steady speed. Since we're moving at a steady speed, we are not changing our speed, so we are not accelerating. So, if we're not accelerating, we are in equilibrium. In this case, we are in dynamic equilibrium. So, let's move on to step 2. Think about what forces are acting on the car. There's 4 of them in this case. Every object has a weight force associated with it near the surface of the Earth, so we have a weight force. We again have a tension force in the rope, but the car is on a surface and it's moving along the surface. Remember that any object on a surface will experience a normal force that pushes back. So there is a normal force here because it's an object on a surface. And there's another force between the surface and the car, and that is friction. It tells you in the problem, but friction is opposing the car's motion as well. So this is visually what the problem looks like. A car being towed with a rope. We have weight, normal force, tension, and friction all acting on this car. So now let's think about how to draw the free body diagram. Weight always points straight down. Normal force always points straight off the surface. Tension points in the direction of the rope, which is up and to the right. And friction opposes the car's motion, so it'll point to the left. In this case, this is the correct version of our free body diagram. Weight downward, normal force up, tension in the direction of the rope, and a friction force resisting the motion. More specifically, because the car is sliding across the surface, this is kinetic friction, F sub k. So that's what we'll leave in our description. Now, there's obviously a lot more happening in this problem. Instead of 2 forces, we have 4, and one of them is at an angle, which adds in another complicating factor, because this basically makes a triangle. Which means, unfortunately for people that don't like trig and vectors, we do have to take into account the x and y components of this vector. So why don't we just real quick write those in. This is the tension force, and this horizontal part of this triangle is the x component of that tension force. So why don't we label that, say, Tx. Now, think about your trig rules, SOHCAHTOA. This is the adjacent side of this triangle. It's the side adjacent to the angle. So comparing that to the hypotenuse, the trig function that uses adjacent and hypotenuse is cosine. So we'll represent this as T cosine theta. I don't know what happened to my pen there, but T cosine theta. That's the x component. Now, the y component, or the vertical component, Ty, well, this is the opposite side of the triangle, right? It's on the opposite side of the angle. So the trig function that uses opposite in a hypotenuse is sine. So this one will be represented as T sine theta. Okay? So just keep that in mind. Using these x and y components of your vector are important if something's at an angle. So that was step 2 of our problem-solving strategy. Now we solve. So again, every problem starts the same way. Write out your laws. Oh, that is a really bad sigma. I'm going to erase that one. Write out your laws in component form. So let's try that again. So we'll have the sum of forces in the x direction and the sum of forces in the y direction. So let's think about what forces are acting in the x direction. There's 2 forces that act in the x direction. The tension, or specifically the x component of the tension, pointing to the right, and the kinetic friction pointing to the left. Remember, to the right is positive, to the left is negative. So we have a positive tension, or T cosine theta, because it points to the right, and a negative friction force, Fk. We are still in equilibrium, so this is equal to 0. Okay, so again, in the x direction, horizontally, we have the x component of tension, or T cosine theta, and friction to the left. In the y direction, vertically, there's actually 3 forces that are acting. We have the vertical component of the tension, the normal force also pointing upward, and then the weight pointing downward. So we have a positive T sine theta for the tension that points upward, plus that positive normal force because it's also pointing upward, and then minus a weight because it's pointing downward. All of that is equal to 0. So here is the setup for our problem. At this point, we solve. It says, what is the tension in the rope? Well, understand that tension shows up in 2 places. So let me just underline here. Tension shows up in both of our equations. So that's what we're trying to solve for. But let's look at what we know. In the first equation, to solve for t, that means we'd have to know everything else in the equation. We do know what the angle theta is, it's 20 degrees, and we are told what the friction force is. So we can actually solve the x equation for tension. Just for curiosity's sake, let's see if we can do that with the y equation. We want to solve for tension, which means we need the angle, which we have, but we don't know what the normal force is, and we also technically don't know what the weight is. We're given the mass. So in the y equation, we don't have the normal force or weight, so we can't solve using the y equation. So that means we are going to use the x equation to solve. So bring that down here. I'm just going to write the equation again. So we have t cosine theta minus friction equals 0. Solving for tension, I will add the friction force to the other side and then divide by cosine theta. So I'll have Fk over cosine theta. Right, just a little bit of algebra. Right, at this point, all we do is plug in and solve. We are told that the friction force is 320 newtons. And we have cosine of the angle, which was given to us as 20 degrees. 320 divided by cosine of 20 should give you something just a little bit bigger. This will end up being, I believe with some rounding perhaps, an answer of 340 newtons as your tension. Okay, so this is very different than the problems we solved in the past, where we'd basically set up the problem with our knowns and then pick the right equation to solve it. Here, we're actually building the equations ourselves by understanding what forces are acting on the object and then writing out the equations based on that. So that's why I've emphasized up until this point how important drawing a free body diagram is. Because without being able to draw the free body diagram, you aren't able to appropriately write out the equations, which means, unfortunately, everything will be incorrect or unsolvable at that point. So be very careful. Okay, at this point, let's do our third and final example for this lecture. This problem comes with a drawing. I'm going to do my best to draw this and the free body diagram. I'm not an artist, and it's hard for me to get used to this drawing pad again. But anyway, a ball weighing 50 newtons is pulled back and held in place by a rope at an angle 20 degrees from the vertical. What is the tension in the pulling rope? So the situation looks something like this. Ignore that. This is like a ceiling. Hanging from this is a rope. Well, where'd my other line go? Okay, you have a ceiling and a ball hanging from a rope, but there's another rope attached to it off to the side that's being pulled. And it said it makes an angle 20 degrees with the vertical, so this is the angle theta. It's not my best work, but you should be able to at least understand the context of the problem based on this. Right, so it's a ball hanging from a rope from the ceiling that's pulled back by 20 degrees by this other rope here on the side. Ask ourselves, is this in equilibrium? Well, it says that the ball is held in place, so it's just being held in place. There's no motion at all, so there's no acceleration, which means we are indeed in equilibrium. Static equilibrium. With this, let's go ahead and draw a free body diagram. So again, I'm doing my best here. So let's draw our axes, x and y, like so. Label your axes and represent your object as a dot at the center. Now we want to identify the forces and draw them in. So in this case, we have a couple forces. Like always, we have a weight. So I'm going to draw a weight pointing down. Right, that's the force due to gravity. But we also have two tensions. There's a tension in the rope pulling to the left and a tension in the rope pulling up and to the right. Let me start with the one pulling to the left. We have a tension here. I'm going to call this one T2. Because there's two tensions, we want to differentiate them. So we'll call this one T2. There's also another tension in that rope pointing kind of upward. Make sure that when you draw this vector, it has about the same height as the weight and the same like horizontal distance as the tension 2 so that everything balances. I'm not going to be able to do that perfectly, but maybe something like that. This is T1. Now, one thing that tends to confuse people is where to put your angle here. In the drawing, our angle is up against the ceiling, but we need to know where to put it here. Well, that is why, if you recall, from our math review, which is I think it was in our second lecture, we talked about how to determine certain angles in different geometries. So understand that this here is the vertical above the ball. And so this angle here is also theta due to opposite interior angles. So the vertical is here, the rope is here, so it's the angle between the vertical and the rope. In other words, the angle between the vertical and the rope. This is your angle theta. So we make our triangle with the y-axis in this case. Okay, so be careful with that. This is why we did a little math review in the beginning to get used to these angles. Your angle is made with the y-axis in this case. While we're at this, why don't we go ahead and look at the components. So let's look at the x component and the y component here. So T1x, the x or horizontal component, is the opposite side of the triangle. And so in this case, it's the opposite side, so we're going to use the sine function. So this is going to be T1 sine of theta. And that's probably the worst arrow I've ever drawn. But over here, the vertical component, or the y component, is the adjacent side of the angle. So we're going to use cosine. So we have T1 cosine of theta. Okay. With this, we can start to solve the problem. As always, write down Newton's second law in component form. The sum of forces in the x direction. Well, looking at our free body diagram, we have the x component of the tension 1, so that is T1 sine theta. That's pointing to the right, so it's positive. And then we have T2, which is pointing to the left, making it negative. Again, we are in equilibrium, so these are equal to 0. The forces balance, in other words. Let's now look at the y direction, the sum of forces in the y direction. Well, we also have two forces. In this case, it's the y component of T1, or T1 cosine theta, minus the weight, which is in the downward direction, so that's why it's negative. Again, in equilibrium, so it's equal to 0. So these are the two equations we want to start working with to solve this problem. Now, we have to be careful. It is asking for us to solve for the tension in the pulling rope, the one that you're pulling on. So it's basically asking for what T2 is. Right? That's the one that's being pulled on. So think about what this means in terms of trying to solve. We want to solve for T2. That's the only place it shows up. So if we have to solve for T2, that means we have to use this equation. In other words, we have to know everything that's in this equation. We know the angle theta, but we don't know what T1 is. So if we don't know what T1 is, we can't solve for T2. So what that means is we have to solve for T1 first. Right? So we have to solve for T1, then solve for T2. So we'll just write this to get T2. This is bad handwriting, I'm so sorry. We must first solve for T1. And T1 can be solved in the y equation. So we'll say via the y equation. I don't know if it's worth me writing all this out, especially with sloppy handwriting. I'm so sorry. So to get T2, we must first solve for T1 via the y equation. So let's do that. Let's solve the y equation. So bringing this down, we will see, I'll just write it again first, T1 cosine theta minus the weight equals 0. We're solving for T1 first. So T1 is equal to the weight divided by cosine of theta. We do know both of these values. The weight is given to us in the problem as 50 newtons. And we do know the angle, cosine of the 20-degree angle that is given to us. 50 divided by cosine of 20 is going to give you a slightly larger number. In this case, I believe that is 53.2. So we'll have 53.2 newtons for T1, based on this y equation that we just solved for. Now we can plug that in. So now we can take the x equation and solve that one. Let me rewrite it here. We have T1 sine theta minus T2 equal to 0. So here we want to solve for T2. So basically you're just taking T2 and adding it to the other side. So we have T2 is equal to T1 sine theta. We do now have both of these values, so we can solve. T1 we just solved for was 53.2 newtons. And then we have sine of theta, which is 20 degrees. So 53.2 sine of 20 will give you, roughly speaking, 18 newtons as your answer for the tension in the pulling rope, in other words, tension T2. Okay, so we have slowly built up these problems. It might have seemed fast, but the first example we did was very basic, just very quick look at, here we go. A very quick look at how to apply these equations, right? Just one step to solve. The next problem, we added in the complication of having 4 forces and 1 at an angle. But still, it was only a single math step to solve the problem. We just had to solve the x equation. That's it. So all we did here was add in more forces and something at an angle. And then in the third example, we added in an additional complication because what we did was make it such that we had to use one equation to solve for something and then plug that into another. So there's not any more forces here than we saw in the last example, but the math involved was a little bit longer because we had to use both equations to get to our answer. And that is actually fairly common, a situation like this. So with this, we are concluding our lecture on equilibrium. In our next lecture, what we're going to do is solve problems where we're not in equilibrium, where there is an acceleration, and you have to take that acceleration into account. So until then, thanks for watching, and have a great day.